Let me introduce the next talk.
I made changes to the schedule.
Could you mute yourself?
Okay, just make the changes and just, or like, oh, just copy that over.
Money. So can you mute?
You want me to just copy that over from the previous one?
Yeah, I think the only change is that
Whoever is
I don't need
hosting,
reliability because you
Yeah,
have
so I think Manny,
Yeah.
please mute, and someone else also.
Right. Okay, yeah.
Okay.
So the next talk will be Dimitri Berenson from University of Michigan. Dimitri has many well-known works in grasping and manipulation. So his talk is about the deformable object manipulation. Let's welcome Dimitri.
Thanks, and sorry to rush people. I know you probably want a coffee break, but I have too many commitments, so I have to kind of stay on schedule. So yeah, I thought that I could talk a little bit about benchmarking for deformable object manipulation. But before that, I know that there are a lot of people here who don't work on deformable object manipulation. So I want to motivate why this is so important, not just for our particular field, but actually for robotics as a whole. So when you ask somebody who works in this field, well, why do you work on deformable object manipulation? The most frequent answer you get is about applications. And this is the easiest story to tell, right? So we have great applications in caring for elderly people, in industry, manufacturing, food preparation, surgery. Awesome, okay? No doubt that these are worthy applications, but that's actually not why I work on this field. It's nice, it's nice to put that in our grant proposals, but really I work on this field for a different reason. And that reason is that I believe we need to be challenging the assumptions that have guided robotics so far. So what do I mean by these assumptions? Well, things like rigidity, known dynamics models, simple uncertainty distributions, assuming fully actuated systems, and so on, right? All of these assumptions, I would argue, have been absolutely critical for us to make the progress we've made so far in robotics. But now they're at a point where they're becoming limiting. And we have to start challenging them and revising them or just removing them if we want to make progress in the future. And so for me, deformable object manipulation is the way to do that. It's maybe not the only way, but to me, this problem is what I call robotics complete, in that if we can solve deformable object manipulation, say create systems that operate on the level of a human for deformable object manipulation, then we will have solved absolutely fundamental perception, planning, control, and probably many other problems as well. So that's why I work on this field, and that's why I think encouraging more people to do this and to challenge these assumptions is important. And one way to do that is creating useful benchmarks. So before I get into what I think about benchmarks in this area, I think I want to draw some lessons from our past work, just so you see kind of where I'm coming from. And of course, I know my own work better than others, so I can highlight, you know, the assumptions and the difficulties we face there. So I'll just do a very brief series of videos on some lessons from our work. So one of the first things we did in this field was to think about how we can do control. And so what you see here are two different methods of doing control for these blue grippers as they're manipulating this green cloth. And the goal is to wrap it around the cylinder and kind of feed it over like that. And what you see in the bottom right is a histogram of which models are being selected for the control action at the given time. And they're selected through a multi-arm bandit process that's looking at the performance of different models across time and correlating model performance. That's not important. For the context of what I'm saying here, what's important is that unlike in a lot of rigid body manipulation where you say, okay, here is a given model of my object and I'm going to assume it works, I'm going to assume some friction model or some dynamics model. I may even put some simple uncertainty distribution on the output of that model, but basically my model is more or less correct. You cannot do that with deformable objects in a very, and achieve general performance across many different tasks. You can, of course, make a specialized model that does well at something, but it's very difficult to create one model that works across many different things. And that is going to impact how we set our benchmarks, and I'll discuss that later. Here's another work from our lab here. Here we have a rope. It's in this very complicated maze environment. It has two levels. There's a bottom level and a top level, and it has to get to this red area over here. And what you just saw there was motion planning. And the motion planner was finding a path for the grippers to get from here to here. And it was using a simplified model of this rope that didn't do full dynamic simulation to actually create an efficient planner that could still avoid obstacles and avoid getting the rope caught on these obstacles, right? So this is also suggesting something that is a little bit different from what you see in rigid body manipulation, is that we need to be thinking about the correct level of abstraction for deformable object manipulation tasks, right? So methods that are focused on, let's say, fine manipulation, as you'll see in a minute, it'll do some fine manipulation, are actually quite different and have very different goals from methods that are focused on long-term manipulation, like a long horizon with a lot of obstacles. Here, what you're seeing is the fine manipulation example where we're iteratively adjusting the gripper positions to make the green rope match the red targets, right? And that's a very, very different process from the global motion planning that you saw before. And that's a characteristic of these kinds of tasks. We can't just think that, okay, just like with rigid body manipulation, we go from a start to a goal. Here, goals level abstraction of goals is itself a key problem. And that, again, is going to define different kinds of benchmarks, because how do you set the goal for the benchmark task? Here's another issue we focused on, perception. And in perception, what we see here is that our method in the upper left is outperforming some other methods in terms of tracking a deformable object, right? So you see here, it's able to account for geometry. You'll see in the next example, it's able to account for self-intersection, whereas other methods don't do that as well. And it's really showing something very important about the problem of deformable object manipulation, because there's so much occlusion and potential for confused self-intersections where, objects can pop through each other or through themselves. Looking at a single frame image and trying to estimate things from a single frame of an image is actually not a good idea for these kinds of tasks. It's much more reasonable to look at sequences of video than single images. So again, that will lead to different kinds of benchmarks where we're not just looking at single images from a system, we're looking at video sequences. Here's just an example of how all these three are integrated in one specific demo. Of course, this demo is just one task, right? Where we're tracking the cloth on the right, and we're doing motion planning to plan that broader high-level path that's going to allow us to get around obstacles. And the execution is kind of slow because our tracking is a little bit slow, and our communication on the robot is a little slow, but those things can be improved with just better implementation. And then when we get here, what you see up here is that the robot is actually trying to finely position the cloth to orient it properly in its goal region. And it gets pretty close, not exactly there. We have a kind of rough goal specification. So this is just one example of how these things can be integrated. Now, again, how do we make benchmarks here? Well, do they need to have this specific robot with this specific sensor and so on? No, that would be asking too much. However, if we get too generic and say, well, you can, just have this camera sensor and you can have this kind of robot that most people have, it's more accessible because then you can run your experiments in the real world. But it's telling you actually a lot less about what methods are useful, because you're restricting many methods that might exploit the geometry or the kinematics of a particular robot. And some of our most recent work is very exciting. We're actually focusing squarely on the problem of having unreliable dynamics and what to do about it. So in this problem, let me start this video over here. We have a mass on the end of a string, and that string is held at this end over here away from the mass, and it swings back and forth. We can swing it back and forth, and the goal is to hit a target, this blue target, without with the mass, but not with the rope itself. Okay, so how are we going to accomplish this? Well, traditionally, you just learn a model with lots of data. But we're saying we don't want to do that. We're assuming small amounts of data because that's what you actually get in the real world. So we train with a variety of simple model parameterization, parameterization of a simple model, which is a cart pole. And then online, we learn where is that simple model valid in the state space, or really in the observation space of a complex object. And we do not assume that we know the state representation of the complex object, right? So all our method is getting is these images. Our method is in the upper left here. And just from these images, it's able to figure out where its dynamics are accurate and where they are not, based on ensemble CNN. Now, here's another application of this method. This is for a rope manipulation task. And again, how do you model a rope? Well, a simplified model is just a rigid link. So what if we train on that simplified model? Can we exploit that model to actually do something useful on a real rope? And as you can see here, when we start out, our method is on the left over here. We're pretty bad at it, but the kind of know nothing approach of both model free and model based RL does much worse with the limited amount of data. And we see that, here by episode 20, we can complete the task. Actually, we completed it with about 80% success rate by this episode. So this is 20 tries. This is nothing in comparison to RL methods that need hundreds or thousands of tries, right? And we can also generalize this from simulation to reality, right? So this is some domain randomization with that rigid link model and simulation. Then we see in reality, we're able to perform quite well with, again, just 20 tries. We get about 80% success rate. And these can be actually pretty tricky. As you can see, the rope gets caught very easily. So what's the point here? The point here is that we're really playing with what is the state representation. Are we going to represent things in terms of images? Are we going to have prior knowledge of some simplified model? That's all up for debate. And that makes comparison across benchmarks that much more difficult. On a benchmark, I should say, across, on a benchmark across methods, that much more difficult. Here's another example where we're learning a simplified model, not hard coding it from data, and then we're deploying that simplified model in a much more complex environment where there are things that it hasn't seen before. And then we're trying to estimate where that model is valid so that we can actually do a kind of long horizon motion planning. The method before was doing more short horizon kind of MPC. And you can see it's manipulating ropes and hoses and stuff like that. This is all planned in simulation and then just executed on the real world, but now we're actually integrating online perception in this. And again, the point here is that we don't know a lot of the behavior of these objects, right? And so we can learn some kind of simplified estimate of the dynamics of the object, but we're not going to know exactly how that object is going to slide on, an obstacle and whether it'll get caught in this particular configuration or not. Okay, so I want to talk just for a little bit about the benchmarks in this field that currently exist. And personally, I'm only aware of two, one of which was literally just published right here at ICRA. Now, if you know others, please post in the chat because I'm very interested in learning more about benchmarks here. And I probably there are others out there that I don't know about. So please post in the chat if you know more. Okay, but the ones I know about are SoftGym and this brand new one that's called Deformable Ravens. And I think this is great because this is giving us a starting point on how to benchmark tasks in deformable object manipulation. But I would argue this is far from the endpoint. And there are other things we need to think about that's outside these kinds of benchmarks. So the first thing we need to think about when creating useful benchmarks for this kind of field is the representation. Now, in a lot of RL methods that are, heavily into benchmarks, the representation is even just is often given up front, or it just takes raw images, right? So you could say that images are kind of the fairest input because they are telling you something that is somewhat model free, right? Now, of course, what sensor using and all that of course affects how you interpret the image data. But still, there's kind of as little domain knowledge and bias in here as possible, you could argue. But we also have to be very careful in that our methods don't overfit to these simulated sensors. And the big problem with simulation is that effects like this, what you see in the real image at the bottom, where you see the shadowing and the spatula is almost impossible to distinguish from the table, right? It's very different from what you see in the simulated depth map up here. And so our methods have to be really careful in that they don't overfit to the simulated sensors. And of course, I know there are noise models that you can introduce into simulated sensing, but I think it's really, really hard to duplicate the kind of noise and problems that you see in real world sensors. So it's not saying we shouldn't do simulated sensing, it's just saying we have to be quite modest about what we can claim when we work with simulated images. Another issue that we have to think about in terms of benchmarks is accessibility versus practicality. So in rigid body manipulation, this is not as much of an issue. And the reason is that for the most part, and I'm not trying to cut anybody out, but if you just look at what's published, most of it is pick and place and to a lesser extent pushing. And then there's a few scattered papers on tool use and kind of more exotic rigid body manipulation, right? But for the most part, I would say 80 to 90% of published work in this area is on pick and place with 10 to 15 being pushing. That's my very, very rough guess, okay? So the thing about these tasks is that you can do them with 1 or 2 arms. You can do it with a Sawyer robot, you can do it with a Wham robot, you can do it with an ABB robot, and everything's kind of okay, right? All of those can do pick and place. In fact, they are built to do pick and place, right? However, in deformable object manipulation, we have many more different kinds of tasks, and also we really need to have 2-arm robots to do a lot of things in practice. Why is this? Because there's too much flexibility in the object. So one arm is often needed to just hold it down while the other arm does something. Now, of course, you can do things still with a single arm. It just becomes much harder and much less practical. So what are our benchmarks going to have? Is there going to be a 1-arm version or a 2-arm version? Are we going to look at methods that exploit the robot morphology, right? Not treating all robots as the same, but actually exploiting the capabilities of certain robot geometries or grippers or whatnot. We have to be very careful that we don't pigeonhole ourselves into a narrow area where things are easy to compare, but actually not that useful in practice. Okay, then there's the question of which tasks should we be benchmarking? And I think when people create a benchmark, there's a kind of underlying assumption that at least a large number of people in the field have reached some kind of consensus on what problems are important, right? And that consensus can emerge and split apart and things change, yes, of course. But at some point, somebody has to say, look, we're all working on the same kind of stuff. Let's have a benchmark, right? And one of the things that I'm a little concerned about with deformable object manipulation is that we don't have that yet. If you look at the tasks that different labs are doing, they're very different, and not just in appearance. They're really quite different kinds of manipulation, and they're making very different assumptions on what is actually known a priori about that manipulation. So for instance, these rope manipulation examples at the top here, very strong work. I mean, not to disparage anybody's work, but they're all doing very, very different things and making very different assumptions. And maybe that's okay. Maybe it's okay to make different assumptions depending on the tasks you're doing and not just treat it as like a giant pixels to torques problem, right? And the rope manipulation people are making very different assumptions from many of the cloth manipulation people. And people manipulating soft tissues, like in the lower right here, are making yet other assumptions, right? And so how do we create benchmarks that are more than just niche tasks and can talk about a broad array of tasks when the assumptions given for those tasks that people are using are so different? Okay, that brings me to the point of having fair comparisons. And so because we make such different assumptions, it becomes very hard to compare different methods because they vary in the type and amount of domain knowledge that's actually used, right? So for our example from the video I showed, right, if I was just running a straight RL method to learn the dynamics of this tethered mass here, it would take a lot of data to actually learn these dynamics accurately, right? And our method assumes a simplified model, which is domain knowledge, right? Actually, eventually we want to automatically pick a simple model from a library, but then even constructing that library is domain knowledge, right? So how can I compare a RL method, which gets no prior data, to one that uses some prior information, even if it's very vague or incomplete? You can't really make that comparison in just a table, right? So I don't want to just be negative and talk about challenges. I want to mention just a couple of prospects. So the first I want to mention is which tasks should we be focusing on? And here I think we really need guidance from industry. We shouldn't have just researchers in academic labs sitting around and saying, hey, this would be a cool task to do. Which honestly is a fair criticism of our work. We maybe should be engaging more with industry when we formulate tasks, although we try our best, but maybe not enough at this point. Now, of course, the industrial real-world tasks can be way too hard to make a simulated benchmark, probably. So what can we do? Well, we'll have to simplify them somewhat, but let's not simplify out all of the interesting complexity. The other thing I'd propose is making an extensible set of benchmarks, and this will allow others to propose benchmarks that can be added to a simulation framework and having a review process to accept and reject them. I don't think the best way to propose new benchmarks is to write papers, for instance, right? I think there can be a more specialized process for that. And then finally, I think we need to have some idea of what's a fair comparison and set our expectations appropriately. So the kinds of apples to apples comparisons where we just make a giant table of competing methods that all have the same assumptions, that is actually not going to work well in our field. The reason is that too many fundamental questions are still unanswered. How much domain knowledge do we use? That's still up for debate. So does that mean we make no comparisons? No, absolutely not. Instead, what we see that benchmark tasks as are demonstrations of useful practical tasks that we might want to do. And as long as we explicitly describe what prior knowledge is used, people can evaluate for themselves whether they have that kind of knowledge for the task they're doing, right? So we take away the nice, easy, and honestly lazy approach of just making a giant table and bolding the things that you're good at, right? We can't do that. However, we do gain a more honest and I would argue more useful presentation of how our method performs. And the final thing I'll say is that we should not be emphasizing the score on a single benchmark task as here's why our method is great. We should be emphasizing applicability over tasks because that speaks to the generality of the methods we're developing. So with that, I'd like to say thank you to the great students in my lab who did all the work in those videos I showed you there and are doing great and very exciting to work with, and also to our sponsors for supporting that work. And I'm happy to take a few questions if anyone has them.
Yeah, thank you for the very nice talk. And actually from now on, Maximo will take over to be the host of this workshop. Maximo.
Hello, everyone. Thanks a lot, Dimitri. Long time no see. Great talk. Actually, on the chat, we pasted a couple of papers about benchmarking deformable object manipulation. one of them actually precisely on this topic of bimanual manipulation. So in particular, bimanual cloth manipulation. So this is actually interesting, and it's one of the things that you touch upon. Do you think that it makes sense to make the difference between what tasks can we solve with one robot arm and what tasks with a dual arm system? Or shall we just place the task and let the people naturally come up with the most relevant solution? What are your thoughts on this?
Yeah, that's a great question. Well, again, my view on it is, what are we trying to present in our research paper, right? So if I'm an industrial automator and my job is to automate tasks, I could care less about benchmarks and stuff. I have a task, I'm going to find the method that is most relevant, and I will buy the equipment necessary within my budget to implement that method. So if I can buy a 2-arm robot and it works better, I'll do that, right? But if we look at our role as researchers, right, then I would argue that we actually don't want to be thinking that way. We should not think about, well, if I have a 2-arm robot, I'll do this. If I have a 1-arm robot, I'll do that. We should be thinking more broadly about, here are the fundamentals of this problem, and here's how I would do my best to solve this problem based on those fundamentals, given a system. And sometimes that system should be a 2-arm robot for the reasons I described. So the use of the 1 or 2-arm robot shouldn't be kind of looked at the output level. It should be more what is necessary to actually perform these tasks, in my opinion.
Cool. Thanks a lot, Dimitri. Is there anyone that wants to ask?
I see a question from Peter.
Yes, hello, Dimitri.
Hello.
Thanks for the talk. I showed up a little bit late. I have a question. So I come from a little bit of industry, and I'm curious if you were to have like the perfect industry partner to help you define these benchmarks, like what types of things would you want to hear? Like what would be like the application form from the industry benchmark representatives to best participate in this community?
Yeah, wonderful question. Yeah, I mean, I think that's a very long conversation, so I'll just give you a quick thing, but let's talk over email and we can flesh it out a little bit more. So first, what I want to emphasize about this kind of industrial inspiration, let's say, for our benchmarks, is not that like industry, like, okay, my task in industry is to like drill screw holes, right? And so I'm going to go to you and I want to benchmark about drilling screw holes. That's fine, but we're not like doing special purpose work for just like a single industrial application. And we're not even going to be that good at it compared to the people whose job it is to do that. So instead, what we need to be doing is engaging groups from across multiple industries and trying to find those common threads of like, okay, well, drilling in a screw is an instance of, let's say, I don't know, peg and hole task or something. And so therefore, let's look for other industrial applications where they use peg and hole tasks and try to engage those people in the conversation. And so then as researchers, we can have an impact on more than just a single niche problem. Right? I would hate to see a bunch of benchmarks that are just like these niche problems and that don't actually promote a broad contribution in this field.
Great. Thanks a lot, Dimitri, once more for your very nice talk.
Thank you.
Look forward to see you in person soon.